5,000 tons of thorium would supply the planet with all of its energy for a year. Every time mankind has been able to access a new source of energy, it has led to profound societal implications. Human beings have had slaves for thousands and thousands of years. And when we learned how to make carbon our slave instead of other human beings, we started to learn how to be able to be civilized people. Thorium has 1,000,000 times the energy density of a carbon-hydrogen bond. What could that mean for human civilization? Because we're not going to run out of this stuff. We will never run out. It is simply too common.
Thorium is a naturally occurring nuclear fuel that is 4 times more common in the Earth's crust than uranium. It's so energy dense that you can hold a lifetime supply of thorium energy in the palm of your hand. We could use thorium about 200 times more efficiently than we're using uranium now. We're still going to need liquid fuels for vehicles and machinery, but we could generate these liquid fuels from the carbon dioxide in the atmosphere and from water, much like nature does. We could generate hydrogen by splitting water and combining it with carbon harvested from CO2 in the atmosphere, making fuels like methanol, ammonia, and dimethyl ether, which could be a direct replacement for diesel fuels. Imagine carbon-neutral gasoline and diesel, sustainable and self-produced.
You can see that uranium-235 is like on par with silver and platinum. Can you imagine burning platinum for energy? And that's what we're doing with our nuclear energy sources today. We're burning this extremely rare stuff, and we're not burning thorium. I ended up at Marshall Space Flight Center at NASA. We were looking at nuclear rockets. Now this time I was not particularly excited about nuclear. In this buddy of mine's office, he got a book on his shelf, and the book was called Fluid Fuel Reactors. And it seemed really different than the kind of nuclear energy we had now. And they also mentioned in this book a lot about thorium. Thorium. 2 spots away from uranium. That's about all I knew. I was like, dude, what the heck is thorium?
This is Kirk Sorensen.
Let me tell you how this stuff was discovered. There was a guy named Glenn Seaborg who worked at Berkeley Labs in California in 1942. This was a guy who had discovered plutonium. And he had, coming off discovering plutonium, he thought, I wonder if we could hit thorium with a neutron and turn it into something. Again, remember, the neutron had been discovered like well, fission had been discovered like 3 years earlier. So they were still in the very beginnings. So he got this grad student, you know. Everybody's been a grad student knows what it's like when a professor says, all right, I want you to go into the nuclear lab and turn on the neutron bombardment system and expose this sample of radioactive material and find out what happens. It's a war right now, isn't it, sir, right? I could be on the front lines. Yes, you could. Okay, yes, sir, absolutely. Off I go. So the grad student went off, and he did the experiment, and he came back to Seaborg, and he said, yep, I've done it, sir. I have made something new. Thorium did absorb the neutron. It became uranium-233. Isn't that cool? Seaborg said, yes, absolutely. Okay, now let's take the next step. Poor little grad student. I want you to go back, and now I want you to hit it with a neutron and see if it will fission, because I think it'll fission. I think it'll fission just like uranium-235. Okay, yes, sir. Goes off, does the experiment, comes back and says, yep, you were right. It did fission. You're correct. It's a new form of nuclear fuel. Then Seaborg popped the really, really, really important question. He said, now I want you to go figure out how many neutrons came off when it fissioned. Because if that number is below 2, we really don't have a story here. If this number, you come back and it says it's like 1.5, then interesting fact goes in the back of the book. But if that number is above 2, then that is a big deal. Goes back, comes back. Sir, the number is 2.5. Seaborg looks at his grad student. This is December 1942, and he said, you've just made a $50 quadrillion discovery. Grad student's like, Seaborg was absolutely right. He had figured out that thorium could serve as an essentially unlimited nuclear fuel. And he knew how abundant thorium was in the crust of the Earth. And he realized that through this process, you could actually sustain the burning of thorium. Now, of course, you're fissioning uranium-233, but you're making a new one.
Weinberg called it burning the rocks. You could literally mine rock just for its energy content.
The power of thorium in a liquid fluoride thorium reactor, if used at these kinds of efficiencies, becomes really mind-boggling. And to try to put this in perspective, I commissioned this animation, the notion of a single cubic meter of regular Earth, anywhere on the planet. By weight,
it will contain roughly 2 cubic centimeters of thorium metal. So if you could extract all the thorium from a regular piece of dirt anywhere, you'd get about 2 cubic centimeters of thorium and about half a cubic centimeter of uranium. If you were to consume that thorium at high efficiency, which is the kind of thing you could potentially do in a lifter, it would be as if that cubic meter of earth had the energy content of 30 cubic meters of crude oil. So this is a remarkable potential capability, the ability to take worthless dirt anywhere in the world and make it worth many multiples of crude oil. I can't think of any industrialist who, if you were to present him with an easily accessible huge pool of crude oil, wouldn't say, yes, let me slurp that up and go sell it to somebody and make a lot of money. You know, here's a way to turn worthless dirt into something worth more than that. But the key is to build a machine that has the ability to very efficiently convert thorium into energy.